So we're going to continue today with HTTP. We learned last time about TCP and UDP and how both exist because we need a couple of different levels of service. You'll find things like UDP used in some surprising ways where people are really intent on cutting some of the red tape out of the way, getting some of the overhead of TCP out of the way. And when you're streaming audio or video, it makes sense. Or running an app where if it doesn't answer you the first time, no harm done. You just send the request again, like you might with a DNS query, for example. But what surprises me is I also see people using UDP where I'm not so sure I agree that if it doesn't answer the first time, it's no big deal. Like with messages to control manufacturing processes or chemical processes, where if it doesn't get received the first time, it could be a big issue. So it's going to be an area of continued research to figure out how we come up with a protocol that's lightweight enough that the message has a chance of being received much more quickly within a millisecond without overhead, but at the same time is reliable. So it's an interesting dilemma that I see people trying to tackle. But today we're going to talk about HTTP, and when we get to HTTP 2.0, we'll get back to the topic again, because that's one of the things that it's trying to decide is whether to stay with TCP or UDP. So there is a special section on this. We'll see how far we get through all of it today. I think it's too much, and I believe in my schedule I have us actually looking at some of this stuff next lecture as well. So HTTP, as you guys probably all know, is a protocol that we use for the World Wide Web, and it's not the first such protocol that was used to bring multimedia objects over, but it's certainly the one that's become most popular. And just to kind of review with you guys again, a web page is comprised of many different items. They're called objects, and there's a base object, which is the HTML file. Most of the time people give it kind of a default name of index.html, and if you just type in a site like google.com and you leave nothing else on there, your system will add HTTPS after a moment, and it'll probably end up adding index.html. Let's see if I can move this around where I need it. Yeah, I'm fighting the drawing tool a little bit. There we go. So this file is the base, and it refers in it. It's a text document, and if you read through it, you'll see links in it to other documents. And if you go and retrieve those documents and you run this HTML file through a parser, it will draw out a page for you using different fonts and putting the text where it needs to go. And these objects will end up as images or other kinds of objects that sit here. Maybe they're video clips, maybe it's a Java window, maybe it's another frame with another web page in it, etc. So the task of building one of these pages is a little bit complex because we have usually multiple files to go and grab at the same time. So if I were to draw this kind of as a hierarchy, I might have my index.html file out here, and some of the items might come from the same website as me, but it's unusual not to have at least some that come from other places as well, like maybe some Google ads that are in there, or if you have other sites with affiliated material, and all these things have to get pulled together and used to build your website. So when you look at a URL, let's break up some parts here. The first part is the host name, and if you bother to supply any other detail after that, it's going to follow a diagonal slash. And in this case, what we see is the rest of a path that looks like it goes down into a subdirectory called some department, and then there's a file in there. And presumably somebody went to grab this particular document at this particular path because it was referenced either by a link on the page, or somebody was given this specific URL to go and type. It would be odd for you to ever to type this in because it's such a specific single object. You would usually go to something a little higher level. All right, a couple of other things on here that are worth pointing out. The last two parts of a host name, regardless of how many other parts there are at the front. So you might have www.central.cs.archive.uh.edu, for example. The last two parts here, the last two parts here, the last two parts in any URL's host name is the domain name. And we'll come back to this in a later chapter. So the domain name basically points to the organization that owns the system that we're going to ask for this content. And the rest of this to the left of the domain name specifies, if needed, which specific host other than the default host we would like for you to try to pull this information from. Everything to the right of the domain name, if it exists, further specifies which web page, which object you want. And if you leave that off, there's a default. And if you leave things off to the left of the domain name, there's usually a default. So I'll show you what I mean. So let's go to our web browser. And we're going to try a few things. So there is a site out there called NewYorkTimes.com, but it's not a web server. It's a host name. But so many people just type nytimes.com that the server or the system that's going to receive this message and try to route it to the server just assumes if I'm trying to come in on a certain port number 80, remember we talked about port numbers last time, that it's a web browser. And so whatever computer really has the website, it will redirect it for us. I don't have to type in the full host name. So nytimes.com is good enough. And you see it got changed to www.nytimes.com, and my connection was upgraded to a secure connection as well. If I were to type in uh.edu, you'll see it gets changed to www.uh.edu. If I type in www.uh.edu, of course, it's going to give me the same page back again. So there's some automatic filling in that's done to try and help those of us who don't really want to spend our lives typing what we feel like are kind of useless parts of things. So by default, from a web browser, which is going to attempt to open a connection at port number 80, if you just type in the domain name, that's usually good enough. If you want something more specific than that, if you don't want the default one for that domain name, let's say you want the one at the computer science department, that's a different URL, and you're going to have to type that one in specifically. But look what it does. Even here, we've been asked to place that under uofh.edu's main website. So this got changed to a sub area called NSM, School of Natural Sciences and Mathematics, and then the computer science department under that specifically. And so here's that web page. Again, the domain name for all of these is uh.edu, but they've put some shortcuts up to try and make it easier for us to type these things in, and then somewhere along the way someone takes care of translating it to the full name. So here's what happens when you type whatever it is you're going to type into a browser. You're going to be running a program that's at the application layer. So if you remember, we have 5 layers: physical, data link, network, transport, and up here at the top is application. When in doubt, assume a program is an application and not one that's running at any other layer, unless you know otherwise. And you'll be right 99% of the time. So here's one of those assumptions we can make. And in fact, HTTP-based programs, including the browsers that you use, run at the application layer. And what they'll do is present some sort of window to you. There's text-only versions of browsers. There's ones that don't have a user interface at all, that just pass messages to with programs and things like that. Usually the ones we use have beautiful window control mechanisms. They have a user interface, and that includes Firefox, Google, Safari, I think it's the same thing as Firefox, Chrome, et cetera, Internet Explorer, the new one that Microsoft has, which I think is Edge. All of those take whatever it is you're doing with your mouse clicks and keyboard strokes, and they convert it into a message. And this message needs to be sent in a packet over the internet. So this message will leave your computer by traveling through the bottom, out the physical layer, as all messages do. It will travel over some link somewhere, and eventually, maybe through a bunch of intermediate routers, it will reach its destination and then travel back up to the top to a waiting companion program, also at the application layer, that is an HTTP compadre, if you will. So if this is my HTTP client, then this would be my HTTP server. So what does it mean to be a client or a server? It just means if I read the detailed specifications on the HTTP protocol, I will find in that both a client and a server described with different responsibilities for both and different finite state machines that govern sort of what messages you are able to send and receive at any given point, what they mean, when you do it, how you react in response to another one, what choices the user has. So the client is the one that's going to usually send things off and expect to get web pages back. All right, so I'm playing the client 99% of the time, and when a server is tapped on the shoulder to receive one of these, it has to already have its server software running and listening for this message to arrive. So these messages are HTTP requests, and what I get back is a response. So this diagram sort of conflicts with one that you'll find used all the time in networking that has time going down the page. This one doesn't. Either that or somebody's figured out how to go backwards in time because this second arrow goes uphill. All they're really trying to show here is not one of these diagrams, but just something that shows you send a request, you get a response back. And when you send the request, there's a lot of other information that's embedded in there that you don't add beyond the URL, things that the browser will attach that describe your environment, the type of system you're on, the brand of browser you're using, the version of it, the language that you're using, the size of your screen, etc., so that the same URL can be sent from a different device, like an iPhone running the Safari browser. And if the server is sophisticated enough, which most are, then it will notice that you're coming from a different device because of that extra information in the request, and it will adjust what it sends you back so as maybe not to overwhelm a small window with a page that the PC giant screen was able to handle, or to send you things that don't require as much bandwidth because you're on a cellular connection instead of Ethernet, for example. So that's basically what's going on. HTTP uses TCP, so if a message is lost somewhere along the way by the network, the browser doesn't usually have to be alerted to that fact because TCP will figure that out and take care of resending the information all on its own. And as I mentioned, there is this thing called a port number, and for HTTP, it's port number 80. And a lot of you may already know that already. So the server has to not only have a web server running, listening on port 80, but TCP is involved because the fact that you're listening on a port number means you've registered your application with TCP and you've asked it to keep an eye open for incoming connections on port 80, and if they get one, please hand you the information. So these messages are exchanged between the application at one end and the application at the other. When you're done exchanging information, then you close the connection. So either you close your browser, which will cause TCP on your system to let the other guy know you're wrapping things up, or the server can get tired of waiting on you to send another message, or it's actually common in early days for servers to answer your question and hang up the phone, basically. They will require, even if you're coming back for the rest of the objects on the page, to open additional connections to get that done. So we'll talk more about that. And HTTP is a protocol that is stateless, which basically means whenever you send it a request, you've got to tell it everything about the request you want, because it doesn't remember anything at all from the last time you asked it something. It did not maintain any kind of information, history, or record of what you did. It didn't keep what we call in computer science as state. So it is not a stateful program, it is a stateless protocol. So what this means is if you pull down a page of HTML and there's an object on there you want to reference, you can't go to the server and say, okay, now give me object 3. The server's going to go, object 3 of what? Well, don't you remember object 3 of the page that you just gave me? What page? You know, the one you gave me a minute ago. Time exists. So it's going to be one of these protocols where if this is the object you want, you have to create a brand new, completely detailed HTTP request that says, dear server, please, if you would, give me the object at this URL, and in this case, it'll be a specific, specific object. So the problem with this is that we, as users, would be frustrated with the program if it never remembered anything about us. Imagine if you went to Amazon's webpage and it never remembered anything about you, the language you speak, the objects you had in your cart, the items that you were looking at last time. That would be a less desirable experience for most people. And some people want to turn some of that off anyway if you don't want to get tracked by Google, for example, and then have the New York Times buy hints from Google as to what things to show in front of you on the advertising part of the web page. Then maybe you'll see less relevant things, and maybe that's okay with you. But most sites aggressively maintain additional information in the background that help them understand who you are and what information you're interested in. So you can't do that with just the HTTP request. You've got to do that a different way, and we'll look at how that gets done. Regardless of the fact that HTTP is stateless versus stateful, there's a couple of different ways we've developed to maintain connections. Non-persistent HTTP and persistent HTTP. And with non-persistent, we grab one object at a time and the server disconnects from you after each one. And that's the way HTTP worked in the very beginning. So if you needed 5 objects to add to your text page, then there were a total of 6 connections that you had to make, 6 TCP connections. And when we get to the TCP chapter, we'll talk more about why that's a problem. So quickly, we enhanced that and basically came up with a version of HTTP where we asked the server software running the HTTP server code to please stop doing that, just to please leave the connection open, because most of the time we are going to be there again in a moment asking for the rest of the objects, and we'd like for you to not force us to kind of go through the whole startup process all over again. So here's an example of non-persistent HTTP. Let's say you enter this URL for the home page of some department at the school that you're interested in. An HTTP client, the browser that you're running, will open a TCP connection, and it will ask for permission to start a conversation. Hey, I've got this user here. He would like to connect to you on port number 80. Do you have any program listening on port 80? And if so, would you mind if we sent you a message? And the server at the other end will say, sure, I'm here. I'm listening. I've been expecting somebody to come, so I will accept your request, and I will send you back something to say, yeah, I'm here, I'm ready for you. What is it you would like to see? So the HTTP client will then send an HTTP request. This is actually where the application layer gets involved. All that's happened up here is TCP sees that your application is trying to open a connection, and it says, hold on a minute, first I have to open a TCP connection, and it does that. And now the application information that your browser generated, TCP will actually send for you. So it hasn't sent anything from the app. It just is trying to quickly set up a connection because it knows you're there and you're anxious to get a connection over. So you'll send the request over here. This is really where the web page request shows up, and the web server will grab the document, the base document, the HTML document, and send it back, and then close the connection. And if you need an object off of that, you look through the HTML that you got back, and you see a reference in here to an image, and let's say there's 10 JPEG images on this page. you're going to have to start over and do this same process again for all 10 objects. So I'm going to back up a page and show you that you'll have to start here. You'll have to open another connection again. You would think it would remember who you are, and you will request, instead of the index.html default homepage for that department up here, instead you will use one of the 10 URLs that you learned about when you got the page a minute ago, and these URLs will be to the images on that page. So you'll have a whole ton of them. With non-persistent HTTP, one big issue is the response time. So it may take a better part of a second for a response to come back, and if you have to wait that amount of time before you can then request your object, and there's 11 total things, including the base file, that's 12 seconds to load your web page. Anybody here want to wait that long? Anybody? Hands? No one? So it's a minimum of 2 round trips, one to open the connection and the other one to get your object, plus whatever the file transmission time is, which is usually small for a web page where you're not downloading a movie, for example. So that's the issue. It takes too long. We don't really want to do that. So what persistent HTTP will do is overcome some of these issues. The overhead of having a bunch of TCP connections open, 2 round-trip delay times, and the fact that to get over this, browsers will often just open multiple TCP connections themselves. What persistent HTTP does is leaves it open after the server sends you a response. It won't hang up on you, and it'll listen for a while. So you can get all of this stuff in as little as a single reference. All right, so let's take a look at the details of an HTTP message here. And 2 types of messages to kind of get the ball rolling. One of them is a request message, and the other one is a response message. So if I want to issue a request to someone, the message looks just like this. You have human-readable ASCII characters. In this case, they're in English. Some of the rest of this can be in a different language, but this protocol is a English language protocol always. So GET, uppercase 3 letters with a space, followed by the name of the file at that host. So where's the host name? Why is the host name not in here? The host name was given to the browser and was handed to TCP, and TCP needed to know it, to know which computer on the internet to go to try and start your connection, to try to request a connection. So TCP uses the name of the host, and it will open that connection up. And when it tells you, I'm ready for you now, you don't need to remind it which host you're talking about anymore. It's already got the connection open and waiting. You just send it which file on there. So anything that took, let's say our example from the University of Houston of uh.edu, anything along the way that sort of changed that to www or changed it to something further down in that stack, in that URL, that's already been done automatically. What you come back with is the name of the file that you would like. There's a space following that. If you type nothing in here, this is what's given by default. So you may not ever type this, but it's always inserted into the GET message. So if you just type uh.edu, then the reason why it knows to go for index.html is because your browser added this in to your request, to your GET message. There's another space, and then there's something that says what version of HTTP you're running so that the parser interprets the language appropriately. And then there's a carriage return and line feed character that indicates that's the end of that first line. Then you have some optional stuff in here, the header lines. This is actually, let me back up here. This is actually where you can specify further the information for the host that you want. So you will find that this gets placed in most of these things, but we'll talk about an example of where I do leave this off. But it's there if you need it. You can tell the server the version of browser that you're running. You can tell the server what you're capable of handling. You can handle HTML text. You can also handle XHTML or XML data that needs to be handed to another application, a helper application, things that would like display JPEG images or PDF files for you without having to leave your browser, the list of languages you can accept, and this is in a detailed syntax that lets you specify lots of different languages here by using this shortcut terminology. And then whether you can handle compressed files or not, sort of encoded files, the character set you can handle. This is something that we talk about in our computer architecture class. The keep alive, how long do you want to keep this connection open? This is a request that you make of the server that says, okay, I would like for this to be a persistent connection. If you don't mind, please don't hang up on me. And if you would keep this open for this long, this will almost always be renegotiated down to a smaller number for you. But between this and asking the connection to stay alive, this is how you request a persistent connection. So this is kind of an important but subtle point right here. Lots has been added to HTTP since the beginning. And instead of making everyone rewrite their servers, maybe there's someone still running, perfectly happy, running an old server that doesn't know anything about persistent connections. It is a completely compliant HTTP server. It's just very old. And the code is okay, code's running, but if you tried to open a special type of persistent connection, it might not recognize what you're talking about. So the method that we've used to add these extra features along the way is by putting them in this list of headers and making them optional. And what we did from the beginning is we taught the server, okay, we know that we're going to be adding things along the way over time, and we know that you may not wish to support them. You may not know what they are. So here's the deal. Keep track of which types of header requests you can parse and deal with, and the rest of them just ignore. Don't blow up your code. Don't crash. Don't send back, I don't know what the heck this is messages. Just ignore them. So if somebody sends you these two types of keyword requests in here, and you don't know what they are, just ignore them. And when the client who has sent this request with these optional 2 rows doesn't get a confirmation back, then he just assumes, I'm not going to have a persistent connection today, I guess. When you're done with the lines, it can be a variable number of lines. You end it with just a carriage return and line feed. So the format basically looks like this. You've got the method. This is where the get was, a space. You have the URL. This was already filled in for us. HTML. There's a space. There's a version here. HTTP 1.1. I think is how, yep, this one was 1.1, and then a carriage return and a line feed. That's all that's on the first line. There's a bunch of header lines, usually optional. Often, though, people will include them because they want the server's help in formatting the content that will appeal to the user. Like, it would be nice if it's in the right language. It would be nice if it didn't include stuff that my browser doesn't know how to render, and if it did include things that it does. And these are basically header field names and then values. So if we go back, header field name of user agent, let me get rid of all this junk. And then value, header field name and then value. And then you finish, and then the rest of this is the body of the message. So for a web server, this would be the actual content of the web page, the HTML if you want. There's another couple of messages worth learning. We learned about get. That's one thing a client can do. Another type of message that a browser can send to a server for processing is called a post message, or using what's called the post method. And this would be a message that gets sent by a browser whenever the user on their web page sees a button like submit and clicks it. And it's associated with fill in the blank fields on the web page. So you can have things that you can click on that just simply take you to other web pages. But when you need to fill something in, like please type in your username or please give me your street address you'd like this package shipped to, and you fill those things in and hit a submit button or take a shortcut like just hitting return in the last one. If the web page author has done their homework well, then what will happen is your browser will generate an HTTP post message. And what that is a message that says post and a space, and there's going to be a URL here again, right? Because if we go back here, that was the rule. After the method, there's a URL. So the URL in this case is going to be this, and actually it'll probably just be this part here. And you'll have a space, and then you'll have the version of HTTP run again, because that's what the protocol says, and then you have a carriage return line feed here. Right, so what is this? Well, you'll notice it has some special characters in here. And so what the web author chose to do of the HTML page here was take advantage of HTML's ability to encode your answers to these fields by, in the background, giving them hidden names of the field, and then taking the contents of this, bundling it up with the name, and then in order, let's say this was the first one and this is the second one, filling in the values that you used, monkeys and banana were the two things you typed in, and separating those with special keys. Actually, that's not quite what's going on in this one. If I read this a little bit better, the field called monkeys, followed by the question mark, was answered or given the value, the contents of banana by the user. So this is how, with the animal search button, please HTTP server, make a note of the fact with this message that I'm sending you as this post message that monkeys, that field, the user typed in the value banana. All right, so that's an example of a method. The URL method uses the get method, etc. Okay, so method types with the original version of HTTP, we had just a few of these. We added some more with HTTP 1.1, including delete. The response that comes back from the web server looks a little different. They don't say get or post or whatever. They're responding. And so they're sending you back, here's a response. It's in this version of HTTP. And the next thing is a status message that will tell you how your request fared. Were they able to satisfy your request? Were they not able to find what you were looking for? Is everything okay? In this case, 200 means everything's good. There's an okay message here as well. And then there's a bunch of information like what time is it? What version of server am I using? The object that you requested was last modified when? There's a special code that it's associated with this object so we can make sure we're talking about the same one. There's some other header information in here about the type and length of the content. Here's a response to your Keep Alive request. I've renegotiated the time down. You need to make sure I hear from you at least every 10 seconds. And in no event will I keep this connection open more than 100 seconds. There's content type, and so here's what I'm about to give you down below. It's text, it's in HTML, and here's the character set, and here it is, blah, 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 blah. Here's the lines here on, sort of what that all looks like. So if I can take a peek here, let me see if I can find something that would be interesting to us to play with. In our page, in our master schedule, we have a couple of interactive animations for this. So I'm going to go share my app, and we're going to take a look at those. Okay, so one of them was the link that I got from the end of chapter exercises, the HTTP get and the HTTP response. So if I go over here and I type in, if I take a look at this code here, I am going to be quizzed on this site to answer the following kinds of questions, such as, what's the name of the file that's being retrieved in this get message? The name of the file is quotation9.htm. And on Windows machines, very often you won't have the L, because in the old days, you had short 3-letter suffixes to indicate the file type. .doc for Word, .xls for Excel, and so forth. And so there's lots of systems that still use that three-letter terminology. Lots of others use four letters. But the name of the file is quotation9.htm. What version of HTTP is the client running? 1.1. What formats of text, images, audio? I'm going to switch to using a cursor here and make this a little bit easier. What formats of text, images, and audio does the client? Okay, got a little thrown off there because I think my audio disappeared on me there for a minute. All right, so we're back on to the slides now, and we've finished taking a look at that site. That site will be helpful to interpreting what's going on in HTTP messages. Other status codes that you may run into once in a while are listed on this page. And if you've ever seen a 404 message from a site that doesn't exist, that one can be kind of fun. I will show you an example of what that looks like here by going to one of my favorite ones. It's always good to find people who have a little sense of humor here. So normally if you go to a site and you want, yeah, that's fine. You want to find something, it's going to pull it up. Normally if you go to a place where there's not a web page, let's say I type in some gibberish here and hit return. Depending on how the site is managed, I may get a custom looking web page, but this one, such as this one, if I try another site, let's try something like this. I'm not even sure that web server exists. Yeah, that's a different problem. Let's try, people are getting more sophisticated, and the default versions of the server software they use are better. Okay, so this one's a not found page. What I am not seeing in these versions of servers is a HTML file coming back that says the magic number is 404. But you'll notice up here at the tab at the top, that's what's coming back. My browser just chose to show it this way. All right, so let's go to Forbes now, and let's try typing in gibberish and see what they see. 40 Forbes. So you can get clever with this stuff. It's kind of cool. But like I say, it's always fun to find somebody with a little bit of sense of humor here. So when you get those messages back, that'll encode it. Now, we can try this ourselves. So what I'm going to do now is open up a Telnet window on a Mac. You'll go to Sherlock, your little search thing, or your applications folder and type in terminal. On Windows, you'll go to your command prompt and type, and you'll do this from there. So let me share this on my Mac, and I'm going to type in. I have to remember to open up this PowerPoint separately because now that I'm sharing the terminal, no one can see the slide anymore, right? So the slide that I want has the instructions on which site to go to. So let's get there and open that up. You won't be able to see this, so I'm just going to use it to cheat a little here. Okay. Telnet to this site. Okay, telnet to gaia.cs.umass.edu. And normally, Telnet will try to connect to a different port number, so I'm going to have to give it the port number here especially. Oh, that's right. Mac got rid of, I knew this. Mac got rid of Telnet. There's actually a lot of change that's going on with Telnet right now on the other things that you can do. So there's other kinds of commands that you can use. I know I have one here loaded. And let's see, let's try it on a Mac. I'll come back to this if I can't find it. You know, the funny thing is it's just infuriated a lot of people, and there's a lot of debate. Some people are defending the move to have gotten rid of Telnet, and because it's considered to be unsecure, et cetera, et cetera. So when you go to try to search for these other commands, which I remember in other versions of Unix more than I do here, it's hard to find it because you have to wade through all of the complaints. Let's see. Yeah, so I'm not finding anything on this page because people are just screaming bloody murder on this side. Here's somebody that tells you how to install it from another location on the internet. I know there's another Telnet tool out here that I've find. I can't remember which ones I've installed before in the past. Have I done this one? Nope, I haven't done that one in here. What about Terminator? Yeah, I'm not having any luck doing this. We'll come back. I'll pull this back up in the next lecture. But you can basically just open a plain text connection to a website. If you do it at the right port number, then you can just type the text commands, the GET space, and the URL just exactly like you would exactly like your browser is doing, for example. So I'm not going to waste any more of your time trying to figure that out. In the middle of the lecture is never the time to try to remember, oh yeah, I didn't do that. So if you've got Telnet on yours, you can type this in, then you can type this command very carefully. This is one line, this is the second line, and what you'll get back is a little hello world from Jim Caroz, the author. Okay, so you remember how I mentioned that we have stateless servers, and as a result of them being stateless, it's hard for the web server to help us out with telling Amazon, hey, I know this guy, he was here a minute ago, why don't you show him the same shopping cart if you want, or here's the web pages of news, here's the news items that he's interested in, why don't you show him those items first in his suggested feed. So there's a couple of ways of overcoming this lack of capability. One of them is with cookies, and the other one is embedding it in URLs. So many websites use cookies. There's a header line of a response message that basically is a request from the server back to the client to please store a cookie. So they'll give you back your web page if that's what you're asking for, but they may ask the web browser if it would mind storing a little bit of additional information about you so that they can remember who you are. And the way this is going to work is you go to a web server and you ask for information. You log in, maybe you navigate to a certain page, and while you're doing this and the web pages are coming back at you from this website, they are taking a little list of like who you were and the web pages you were looking at, things that they would use to remember you later, and they're including those in the objects that they're sending back. And so if you were to inspect the HTTP response message, you would notice that there's a line in there for cookies, and then there's a file, for example, that they want you to store, or information they want you to store. And so what will happen back on your server, on your computer, is your web page will come up with what you want, but in the meantime, in the background, there's also this little file, a cookie, that's being stored on your hard drive. And when you turn back around again, and you click on a link here, or you come back to the page later and you go back to the server, this cookie is going to be sent along with it. So the browser and the server work with each other on getting that kind of stuff done. Right? So this cookie will go back. Inside the cookie is the information that the server had asked you to store, and it will say, Kevin, all right, you had this in your cart, you were looking at this page, etc. So this is how you don't start over from the home page as if you've never been to the site before with every single site you ever go to. So cookies are one way to do this. On the server side, what's happening is your request comes in using HTTP. It hits an Apache web server, let's say. The web server doesn't know who you are, doesn't care who you are. It will, however, pass this little cookie information along, but the web server doesn't do anything with it. The web server does not remember state. So there's usually a massive database in the background that's being used to build your web pages on the fly and assemble things in the right language and paint your pages, get the objects that you need. Maybe they're pulling items from a big database or from a mainframe system. If it's like JCPenney's, maybe they're going to an old mainframe to get the list of the sizes that they have for the pair of shoes you're looking at. Web servers aren't going to store all that stuff. Most of your web pages are built live on the fly and handed back to something that parses it, turns it back into HTML, and then gives it to the web server just for the mechanics of getting it back across the internet to you. And one of the things that they're going to hand to this server to get back across the connection to you is this cookie. So all of that storage of who you are and everything is happening in some big, usually mainframe system for a large company in the background. The only thing the web server is doing is just the mechanics. So to the corporations that sell you things, the web server is nothing other than a tool for displaying information and handing back requests. It doesn't hold any content. It's just a middle piece of software. All of the content is stored in other types of more capable software systems on large computers, servers, etc. So remember, most pages are built live on the fly and then handed complete to the web server as a completed HTML file to be sent back across the network to you. So these cookies are handed along with it because the server won't remember you. And this is the way of this system basically keeping track. It can't get the server to remember you, so what it's going to do is hand you the cookie, and then you hand it back. So you've got to keep track of yourself and get that information back to help that site out. It's an odd way of doing things, but it works. It's elegant and has been worked out. And there's usually hundreds of cookies, sometimes from a single site, that get stored, and I'll have an exercise for you and homework to walk you through looking at where the cookies are and how to count them and find them, and hopefully it'll go better than my Telnet demonstration did today. So here's an example with eBay. The client sends a usual HTTP request message, and it sends it over to Amazon. So forget eBay for a second. This is a cookie that's sitting on my server. but that's not who I'm really trying to connect to today. So I don't know why Jim did this. It's a little confusing. I'm opening a connection today to Amazon. So I go there, I log in, Amazon creates a server ID, it pulls some information out of a backend database for me, and when it gives me the answer back, let's say the initial web page, one of the things it's going to do is include this in the response. Keyword set cookie value 1678. And what my web browser will do is add this cookie to the list of cookies that it already had. And the one that it had before was eBay. Then you go back to Amazon again, maybe just an instant later. The cookie is going to be included because when you go to Amazon.com again, your browser will automatically rummage through the cookies to see if there's a cookie for Amazon.com. And if there is, it will assume the server would probably like to see it. So it will send the cookie back, and this time the web server will say, you again. And so this keeps getting bounced back and forth. They can add cookies to this. Some cookies are big, some cookies are small. In the early days, there were horror stories about people putting your password in the cookie so they could automatically log you in when you came back to them again, and doing so in plain text. So if you just went to your cookies folder and started looking through the files, you'd see the people's passwords in there that had used the computer. So we've gotten a lot more sophisticated with that, but there's some caution that's prudent when using cookies. So you do need to be aware of privacy features, et cetera. The problem is without cookies, your browsing experience is going to be pretty much miserable. It's going to be like starting over with a reboot every time. And it's how we keep state, right? They carry information that helps us keep state. One other big key thing that we want to make sure we go through here is how other servers along the way keep parts of the web pages that you're looking for to relieve some of the burden from the ultimate web server. I mean, think about it. You've got a million users out here. They're all trying to get to a site, and that takes time. It uses network resources, and it's a big burden on this server. So early on, we figured out that to follow the golden rule that I mentioned, send as little information as possible on the network, as short a distance as possible on the network, we started putting devices in here that would keep copies of things. It's sort of like you're sitting here watching somebody go by, every day, and you're sitting on the front porch of a gas station in the country, and you see kids going to school to the right, and you see them coming home from the left, and you have nothing to do with the school, but somebody stops one day and says, hey, do you know where the school is? Even if no one's ever talked to you before, you know what to tell them because you've just been observing what's been going on. And so you can tell them, yes, the school's there. Or if they ask you something more specific, like, what color uniform do the kids wear that go to this school? You can tell them white. The person doesn't need to go to the school now to figure that out. They have their answer. You've observed it and witnessed it. Now, that's okay unless they changed their uniform color last week while you were on vacation for a while, in which case your information was accurate at one point, but now it's out of date. So we do the same type of observation all the time for web pages, and we use web caching servers to do it. And so the idea here is to satisfy a client request without having to go all the way back to the origin. So you're going to keep copies of things that come back from the servers and all the little objects. You're going to keep copies of these things and hand them back to the user. So when the user sends their request over for all these objects, 20 different things, maybe 18 of them, you can hand back to them immediately, locally, without them having to go all the way back to the server for all of them. Maybe a couple of them they need to go all the way back. You can't do it. So here's the idea. This proxy server sits invisibly between you and me. You are the server and I am the browser in this case. So when I send you an HTTP request, it gets passed through the proxy server. Routers will enforce this rule, and there's usually a proxy server locally at your institution. Turns out your browser itself has a web cache built into it as well. So that's the first place it's going to get looked is, do I already have this object? If not there, then it'll send it out towards the web server, let's say it's the New York Times, whatever it might be, and there could be dozens of web caches along the way, run by your institution, by your ISP, by other ISPs along the way, by the destination that keeps you away from the real server, et cetera. And the idea is first person gets there, they go all the way to the what's called the origin server. The next person goes, they don't need to go any further because the information they want is right here. So as long as you're careful and you don't keep information that's out of date, this blue versus white uniform, then it'll work well. So why do we do it? To reduce traffic, to allow websites who become popular but don't have a lot of resources, maybe they don't have giant servers, to keep them from having to constantly upgrade. Suppose somebody gets named as the poet laureate for the United States and they're on the news, and all of their poems are on a little publisher website that's on a PC somewhere in Minnesota, right? And 10,000 people now are trying to get there. Google picks up on it. They list it. It shows up on a feed. It starts to go viral. That PC can't handle the load. So web caching servers will automatically be caching their stuff along with everybody else's that they see. And if a school teacher tells all 30 students the next morning, let's all open our browser to this poetry website, only the first kid in will actually pull the request. The remaining 29 students will find that they won't know it, but in fact the poem will be given to them by the copy that was just stored on the school's cache. Right? So that's kind of the idea. So they go through some math in this example of where you've got an internet link here and users with a certain type of load, average data rate, the delay to each server, and you've got a big fat LAN, but if these users are all going out to these various servers here, see if I can get this to draw for me, then your network is going to be saturated. So everyone's going to be going over this relatively small link, beating its brains out, all trying to get to these servers out here in the end. So one thing you could do is upgrade the server. The problem with that is it's extraordinarily expensive, but it will work. It'll lower the response time down significantly from seconds to from 2 seconds here and then maybe a minute to get through this congestion down to just milliseconds. The problem is it's very expensive. The other thing you can do is drop a local web cache in here and then pull your information in that way. So what will happen is one user will go out and every time there's objects that come back, if the objects don't have something about them that makes it a bad idea to cache them, then you'll put a copy in your local cache. And on an object-by-object basis, the web server can specify whether they want an object cached and for how long. So if they know that it's something that's probably not going to change very often, then they can give it a relatively longer time. So in this example, we cut our utilization down significantly, and some of the objects still came from the servers, but it's now blended. 40% were satisfied at the local cache, which is a much better situation that you want to be in. So it's cheaper, and you get a faster response time. So you remember back that conditional get that we looked at earlier, that if modified sense, where the browser was asking for something, but they said in there only if it's been changed since today at this particular time. Conditional get is a way of making sure the objects that you're loading on the page still are updated. So what a cache or you could do is, instead of going and getting the objects again, just send something small. Send a request to the server that says, hey, I'm trying to load this object and I have a copy in cache, but it's 8 minutes old. Is that still the current version? Is that still okay? Or is there a newer one you'd like to send me? So that's a lot less load on the network than insisting that they hand you a big image every single time. So that's a kind of a go-between as well to make sure things aren't too old. So we're going to end by me going back to the New York Times website. And no, I don't want to do that. Let's go here. And I want to ask you about the objects. There's dozens and dozens of objects on this page. Which ones of them can be cached? Well, the New York Times logo up at the top, that certainly could be cached because that's something that Doesn't change, very, very often, right? So that maybe changes once a year. So if I'm the New York Times and I'm sending all these objects back, when I send this one back, I might say this one's good for 24 hours. And these are good as well. And this is good for that amount of time also. This gets pulled live every time. This is good for an hour. This is pulled live every time. This is pulled, I don't know, this is a key page. It's your top news item. How often do you want people to come back to you and hit your web server up for this content? How often is it going to change? Well, if you're the New York Times, you know how often this is going to change. Yes, it could be breaking news, an attack, something, nuclear explosion somewhere, some sort of emergency in the White House, for example, where you want to immediately have people do it. But maybe what you do is something in between. You tell people, cache this for an hour, but also ask me if it's been updated. So please ask if it's been modified since. And after an hour, I'm going to ask you to do that. Maybe I do it. You can have some policy rules here. You can sort of set this up. So it's quite an interesting way. The idea here is to reduce the load on the internet. You don't want to have to go and get all of every page every single time. Okay, guys, that's it for today. Hope there wasn't too bad of a glitch in there. Lost my video, which you guys can't see on recordings with MP4 files anyway, but it concerns me about about my next live lecture, so I'll be diving into that. All right, have a great one, and I will talk to you guys tomorrow. Bye.